Good day, everyone. And so let's proceed to our first topic or first lesson. We have introduction to matrix. So the objective of this lesson is after reading this lesson or chapter, you should able to number one, define what is matrix, identify all special types of matrices, and identify whether the two matrices are equal. So what does a matrix look like? So matrices are everywhere. So if you have used an Excel program or written numbers in a table, so you have used a matrix. So matrices make presentation of numbers clearer and make calculation easier to program. So look at the matrix below. So this is the sale of tires in a blowout rust store given by quarter and make of tire. So this is an example of matrix. So this is for tire stone. 25 for first quarter. This is the sale. So for quarter 2, so 20. Then Q3 or quarter 3 ay 3. Then fourth quarter we have 2. Then for Michigan, we have 5 for first quarter, then second quarter is 10, third quarter is 15, and quarter 4 is 25. While copper tires, well, we have 6 for Q1, 16 for Q2, then Q3 is 7, then Q4 is 27. So if one wants to know how many copper stars were sold in fourth quarter, so we go along with raw copper and column Q4. So this is the row which is consider the type of tires. So we have 25, that is row 1. Then we have row 2 for Michigan and copper is row 3. So the column will be quarter. So quarter 1, so these are the sales in quarter 1 of different uh, tires. Then we have Q2, quarter 2, quarter 3, and quarter 4. Okay, so what is a matrix? So a matrix is a rectangular array of elements. So the elements can be symbolic expressions or and numbers. So matrix A is denoted by, so this A. Then we have a set of array of elements. So elements or entry. So we can use the word entry or elements for each this A11, A12, and so on, A12, A21. So 1 and 2 denoted as what row or what column it is. So let's say example 1, A11. So that is first row and first column. So A12 is first row and second column. The same as A21, we have second row and first column. So row I of A are the n elements and it is AI1, AI2, AIN. So that is the row element. Then we have column J. So this is the column 1, column 2, column 3, and column M. So yon. Next is each matrix has rows and columns, and this defines as the size of the matrix. So if the matrix A has m rows and n columns, so the size of the matrix is denoted by m by n. So the matrix A may also be denoted as by, or we have A, then we have m times n. So this is the size of that matrix A to show that the matrix A is a matrix with m rows and n columns. Then we have entry. So what is entry? So each entry in the matrix is called entry or elements of the matrix, and it is denoted by Aij. where I is the row number and J is the column number. So we can identify each element or entry by just uh, using the I row or and the J column. So let's say example, A to 1. So meaning that is what is the element in that row 2 and column 1. That is A to 1. So the matrix of buyers, sales, example, could be denoted by matrix A. So this is the matrix A. So there are 3 rows and 4 columns. So this is the first row, second row, third row. Then we have first column, second, third, and fourth column. So the size of this matrix is 3 by 4. So in the above matrix, so A34. So A3 and 1, 2, 3, 4. So this is the A34. So another example would say, let's say A33. So we have third row and third column. So we have 7. So that is the elements of matrix. So what are the special types of matrices? So we have different types. So number one, so we have a row vector or and column vector. So when we say vector or row vector or column vector, that is a matrix that has only one row or one column. So for row vector, so we have only one row, while for column vector, we have only one column. So these are the examples of a row vector and for column vector. So they have it's only one column and one row. Next is what is a submatrix? So if some rows or and columns of a matrix are deleted, the remaining matrix is called the submatrix of A. So let's say example, find the matrices, submatrices of the matrix A. So it says that if some rows or and, so meaning you can delete some rows or and columns at the same time. So let's say example, so this is a submatrix itself if you are not going to delete any of the row of columns, so that is a submatrix. Okay, submatrix. Then if you delete this third column, so the resulting matrix 4, 6, 3, -1 is also a submatrix. Then if you delete this second row, so the resulting matrix is 4, 6, 2, and it is a submatrix. The same as when you delete this second and third column, this at the same time, the second row. So the resulting matrix is 4 only, and this is also a submatrix. Another is when you delete this first column and second column, so the resulting matrix is 2, 2, and this is also a submatrix of A. So can you find other submatrix of A? So just write your answer. Next, how about square matrix? So when we say square matrix, so if the number of rows is equal to the number of columns, so meaning it is the M by N. So your M is equals to N. So M is equals to N. Then it is called square matrix. So the entries A11, A22, meaning that is first column, first row, second column, second row, or second row, second column, and so on. They are called the diagonal elements. So this part of the matrix like 25, 10, and 7, that is the diagonal elements or diagonal entry or principal or main of the matrix. So we have A11, A22, and A33. And this is a 3 by 3 square matrix. Next is the upper triangular matrix. So this is applicable for a square matrix where the number of columns is equal to the number of rows and which your Aij is equals to 0 and I is greater than j. It means that your row is greater than the number of columns or the number in the or the position in your matrix. So that is called the upper triangular matrix. So this is the example. So this is a upper triangular matrix because of Aij is equals to 0. I is greater than j, meaning that is, let's say Aij. So I is greater than j. So this is to 1. Out. Greater than. So this is a, this is 1, 2, 2, 1. Okay. So this is 2, 1. So 2 is greater than 1. Then this is 3, 1. And this is 3, 2. So this part or this entry in 2, 1, 3, 1, and 3, 2 are all 0 because of this condition to satisfy the upper triangular matrix. Next is lower triangular matrix. So this is the reverse where your j is greater than I, meaning this portion, the 1, 2, 1, 3, and 2, 3 are all 0. That is a lower triangular matrix. Next, diagonal matrix. So diagonal matrix where the zeros in upper and lower triangular matrix are all zeros. So this portion and this part is 0. And we have non-zero here in their diagonal. But although we have also considered diagonal entries, so we have, let's say, in the 3, 3, we have 0. So this will be also considered diagonal matrix since uh, the upper and the lower triangular are zeros. Next, what is identity matrix? So a diagonal matrix with all diagonals elements equal to 1. So that is the identity matrix. The rest elements are zeros. This is the example of identity matrix. Next, what is zero matrix? So a zero matrix whose all entries are 0. So these are the examples of zero matrix. So all entries, all elements in the matrix are all 0. Next, how about the tridiagonal matrices? So a tridiagonal matrices is a square matrix in which all the elements not on the following are zeros. So these are not non-zero or not 0. So we have the major diagonal. So the major diagonal is the A11 or the main diagonal. A11, A22, A23, A33, A22, A44. So that is the major diagonal. Next is the diagonal above and the diagonal below. So this is the example of tri-diagonal matrix. So non-zero is the main diagonal. The diagonal is non-zero, the same as the upper and the lower. Although the lower diagonal it has zero, but we can consider it since they are not all non-zero. Not all are non-zero. Okay, so that is tri-diagonal. And this is applicable for 4B, 4, and so on. Because when it is a 3 by 3, it's almost, okay, so you can consider it since we have 0 on the 3, 1, and 1, 3. So, do non-zero matrices have diagonal entries? Yes. So because in NMN, so we consider diagonal entries of A11, A22, A33, and so on until the minimum number of rows or column. So let's try this. So we have A11 and A22. So we have two diagonal elements in matrix A in example number 11. So this diagonal dominant matrix, so NMA, oh, so this is a square matrix, is diagonal dominant if, so we can consider a certain square matrix a diagonally dominant matrix if, number one is, its diagonal or its element in the diagonal is greater than equal to, or the absolute value. The absolute value of the diagonal element is greater than equal to the sum of the elements in that rows or column. Sorry, rows only. So that is I. So meaning that is in the rows, in each row. So, sabi dito, for each row, the absolute value of the diagonal element must be greater than or equal to the sum. Okay, so summation. The sum of the absolute values of the rest of the elements on that row. Okay? So, diagonally dominant matrices are important in ensuring the convergence in iterative scheme in solving simultaneous linear equation. So, this diagonally dominant matrix is applicable especially in iterative solution in simultaneous linear equation like Gauss elimination and Gauss-Seidel, Jacobi method. Okay, so let's try this example if it is a diagonally dominant matrix, matrices. So first is the main diagonal here is 15, negative 4, and 6. So first is let's try this 15, 6, and 7. So the main diagonal is 15, so the absolute value of that diagonal element, so we have 15, is greater than or equal to the sum of the absolute of the rest. So we have 15 is greater than equal to 6 plus 7. So 6 plus 7 is 13 and 15 is greater than 13. So this element 15 is diagonally dominant. So for next is for second row, we have 4. So the absolute value of negative 4 is 4. So 4 is greater than equal to 2 plus 2. So we have equals. So it satisfy the rules or condition of diagonally dominant matrix. So this is dominant. Next is the row 3. So we have 6 and 3, 2. So 6 is greater than equal to 2 plus 3. So we have 6 is greater than 5. So this is also a diagonally dominant matrices. So all the 3 rows satisfies the condition. So meaning matrices this matrix is diagonally dominant. So this is the solution of each row. So we have 15 must be greater than 13, 4 is equal, and 6 is greater than 5. Okay, so these are other example. We have negative 15, 6, 9. So 15 is greater than equal to 15. So that is correct. So 4 is the same. Then we have 5.001. Yan. So if it is restricted in greater than 1, so we have to make some adjustment, 0.001. But it is also equal to greater than or equal to. They're the same. So let's say this equation. So this equation only satisfy for row number 1. But for row number 2 and 3, so that is not satisfied with the not diagonally dominant. So not satisfied with 2 and 3 rows. So this is considered a not diagonally dominant. So when are two matrices considered equal? So we can consider only the two matrices equal if and only if the two matrices are equal in size and the entry or element in its position in that matrix are also equal. So let's say this example. So we can consider A and B are equals if and if only the element in B11 is equals to the element in A11. The same as in B22. So the same element with A22. So two matrices A and B will be equal if B11, so 2 and B22. So we have A the same as in A11 and B22. Okay, so that's all for introduction.